Math Humans. We're going to do 6.3 today. We're going to be talking about Euler's circuits. So our objectives are that we're going to manage Euler's circuits. So notice that it's not pronounced Euler, it's pronounced Euler's. So an Euler's path is we're going to hit every edge once and only once. So this is the key component about an Euler's path. Instead of looking for the cheapest path, our goal is to hit every single edge, but we're going to only hit them once. Another thing that's important is that you show the arrows on for your direction of travel. So then the last definition that we have for today is an Euler's circuit. And actually, I lied. We have some more definitions later, but for right now, it's a nice, easy start. An Euler's circuit is a path that returns to the beginning, because that's always what a circuit is. A path are the edges. A circuit is back to the beginning. So let's do our first example. Okay, so we're going to have a nice little circuit, a nice little graph, and we want to find an Euler's path. So just because I'm going to start at F, and so I'm going to write F down because that's my first letter, and it's important to write it down because then you don't have to go back and try to remember what you did. So then I'm going to go to A, and remember a path means I have to touch every single edge, and then I'm going to go to B, and then I'm going to go to C, and then my next stop is I'm going to go back to F. It's okay if I touch a vertex more than once. It's not okay to touch an edge more than once. My next stop is going to be E, and then I'm going to go back to C, and then I'm going to do D, and then my last one is E. So remember, I can touch a vertex more than one time, like F has been touched 3 times, C has been touched 3 times, E has been touched 3 times, but I can't touch an edge more than once. Alrighty, so that was kind of a cool example. Let's move on to our second example. And in this one, now instead of finding a path, we want to find an Euler's circuit. So on this one, notice that I have kind of this cool little bridge going on in the middle. And it's the same basic diagram, except we've removed this piece, and now I have this entertaining point in the second. So remember that for an Euler's circuit, I want to touch every edge once, and then I want to go back to the beginning. So again, just like on the last one, and for no super clear reason, I'm going to start at E. So my next stop is A, okay, and then I'm going to go to B. So there's my next one. And then I'm going to go to F, okay? So now I'm going to do one of these little loopy guys, and so I'm going to go up here. Remember, it doesn't matter if I hit a vertex more than once. And then I'm going to go back to F, okay? And then I'm going to go to D, and then I'm going to go to C, and then I'm going to go back up to E, alrighty? So this will be an entertaining process, but you always want to make sure, A, that you show your arrows to show the direction. Notice that I started and ended with E, so I made a circuit. I got back to the beginning, and I touched each edge only one time, which is the criteria for an Euler circuit. So now we have a couple little definitions that we're going to work through, and they're called Euler's theorems. So let's just start with this one. So for our first Euler's theorem, it says if a graph is connected and has all vertices with an odd degree. So remember that a degree is how many different things come into the particular graph. Alrighty, so notice like at A is a 2 degree, B is a 2 degree, F would be a 1, 2, 3, 4 degree. Okay, so the first Euler's theorem says if a graph is connected and all of the vertices, this is important, have an odd degree, then there is no Euler circuit. So let's look at this one. We were able to find an Euler circuit, but this one is even, this one is even, even, and even. These two are the only two that are odd, therefore it wasn't all, so that meant that we could find an Euler circuit. The next one says, if the graph is connected and has all vertices with an even degree, then it has at least one Euler circuit and often more. So in this case, I had two odd vertices, but in this one, if all of the vertices are even, then it has at least one Euler circuit. So if we're managing our graphs, one of the very first things that we're going to want to do is look for the degree at each vertex, because that will help us determine if there is an Euler circuit or if there are multiples. Okay? The second Euler circuit, we'll just take it one thing at a time, says if a graph has more than two vertices of an odd degree, then it can't have an Euler's path. Well, if we go back and look at the example that you can't see, I'll pull it down just a little bit, we only had two, so it wasn't more than two, it was two, so then it's still, that's why we were able to find our Euler circuit, okay? And then this last one says, if a graph is connected and has exactly two vertices of odd degree, then it has at least one, often more, Euler's path, and then the path must start at an odd degree and end at the other odd degree. So remember, a path is not returning to the starting place, but if you'll notice what we did in both of these, we started where at the vertex that had an odd degree. So that's kind of interesting. So these are going to be rules that you'll want to have handy as we go through and work on our graphs to make sure that you understand what your possibilities are. All right, Euler's circuit number 3 says that the sum of the degrees of all of the vertices of a graph is twice the number of edges. So that one's not super critical, but it's kind of entertaining. Okay, so now let's talk about how to find an Euler circuit. So I'm just going to go ahead and put these four up there. So number one, it says if I want to find an Euler circuit, I'm going to start and end at the same place, which is what defines every circuit. And for an Euler circuit, I can only hit each edge once. So this is the thing that makes Euler's circuit or paths a little bit different from others. First thing, just like we talked about, is make sure every vertex has an even degree. And then I can begin at any vertex, and I can never use an edge that is the only connection to a part of the network that I haven't visited. Meaning, and so sometimes when we're doing these, it's going to take multiple attempts to find your circuit, and so you may want to recreate the drawing somewhere so that you can practice. But this says, don't go over a bridge of no return, okay? And then number 4 is label the edges in the order that you travel them. So that's what I was doing when I wrote down we started at E and then maybe we went to F. So if you write as you go and include your direction arrows, that means you'll have less work to do when you're done. Alrighty, so now let's look at this one. So this one is pretty entertaining. So the first thing that we're going to do is check our vertices. And so I'm going to write down A, 1, 2, 3, 4. It has 4. B, 1, 2, 3, 4, has 4. C, 1, 2, 3, 4. D, 1, 2, 3, 4. This is kind of a cool looking one. E has, I'm going to put a dot there so I remember where I started. 1, 2, 3, 4, 5, 6. And then F, the last one, has 4. So these are all even, okay? So just because I'm going to choose to start at A, alrighty? And remember that we're going to label as we go. And so I'm not going to pretend that I could have done this on the first try. It probably would have taken me multiple attempts, but this is an attempt that we've already found to be true. So the first thing I'm going to do is I'm going to go to E. So I started at A, and I'm going to go to E, and then number 2 is I'm going to come, and you could put a 1 there, and you could put a 2 there. So I'm going to go back to A, and then for 3, I'm going to come over here, and I'm going to write B. And then for number 4, I'm going to go to C. And then for 5, I'm going to go back to B. remember the goal is to hit every edge once and only once. And then I'm going to go this way. Here is 6 and E. My next one, I'm going to come here, and this is 7. So I went to C. And then I'm going to go to D. Here's 8. And then I'm going to go to E. Here's 9. I still have this piece to get to, and then I'm going to get back to, because we're looking for an Euler circuit, in case I didn't make that clear, my bad. So the next one I'm going to do is I did this one. I didn't write it down, though, so I went from C to D, and then I went to E. Now I'm going to go to F, so this is 10, and then I'm going to go to D. This is 11. And then I'm going to come back to F. This is 12. And then I'm going to go to A. And now I have completed the circuit, and it was 13 different edges. So that's actually kind of cool. Okay? So things to remember. It doesn't, sorry, let me start over. I always want to check my vertices first to see how many are even, how many are odd, because that determines whether or not the circuit is possible. Number 2, it really doesn't matter where I start, and I can hit a vertex multiple times. So notice in this one that I hit it all 4 times, and that's okay, but I can only hit each edge once. All right, so I've made us a little summary at the end. An Euler circuit says all vertices are going to have an even degree. Okay, that means that there's at least one Euler circuit. An Euler's path is going to be possible if there's 1 or 2 odd vertices, and then the rest are even. If there's greater than 2, then there's no path, so that's also a criteria. And then what's never possible for neither, either the path or the circuit, is if it's more than 2 odd. So this is a nice short set of rules to have handy when you're trying to find an Euler circuit. All right, my dears, that is it for today. I will see you soon.